Hi, grade 12s. This is Mr. Musklo, and in this video, we're going to learn how to name alkanes. Now, you might remember from Friday's lesson what alkanes are. They're basically a type of hydrocarbon, and we learned on Friday that hydrocarbons are molecules that contain hydrogen and carbon. Okay, so if you just think about the name hydrocarbon, hydro is referring to hydrogen, and then carbon is, of course, referring to carbon. So hydrocarbons are molecules that contain hydrogen and carbon. And we learned on Friday that alkanes are a specific type of hydrocarbon. Alkanes are hydrocarbons that only have single bonds. Okay, so in any of the examples that we do in this handout, there are only going to be single bonds in any of these structures. Now, we saw on Friday that alkanes, despite sounding quite simple, just being molecules with carbon and hydrogen and only having single bonds, they really can have quite complicated structures. You can have straight chain alkanes or branched chain alkanes. You can also have what are called cycloalkanes, which are alkanes where the carbons are bonded into a ring. And so really there are like millions of different alkanes that you could imagine. And so chemists therefore need a precise set of rules for naming alkanes. The idea here being that if a chemist had a structural drawing for an alkane, they could write a precise name for that alkane following the rules that we're going to learn today. And then they could pass that name off to another chemist, and the chemist could use that name to recreate the exact same structure. Okay, so the idea here is that for any organic molecule, everyone should end up getting the same name if we're following the rules properly. Now, I'm just going to give you a heads up that this is kind of a long lesson because there are a lot of rules for us to remember. But I just want to reassure you that it may seem like there is a lot of information in today's lesson, and there is, but whenever we learn how to name other types of organic molecules in the future, you'll see that we're not going to be learning as many rules. The reason why there are so many rules to learn in today's lesson is simply because you don't know how to name organic molecules at all. So we just need to learn the basics of how it works. In future lessons, whenever we learn how to name other types of organic molecules, you'll see it's really just like slight changes to certain rules. It's not really like we have to learn a bunch of information like in today's lesson. And I'll also just comment before we get going here that I find that this topic is kind of like you love it or hate it. It's kind of a polarizing topic. Some students do actually quite like it because they almost think of it as being like solving a puzzle. You're just given an alkane and then you follow some rules and get a particular name. And whenever you get the correct name, it's kind of satisfying, like solving a puzzle. And for that reason, I kind of like it too. I think it's kind of fun. But there are some students that also really don't like it because there are a lot of rules to remember. So, yeah, you'll find that when it comes to naming alkanes, it's just something that you get better at by doing a lot of practice at it. So we're going to go through 4 examples in this handout. You'll have an opportunity to do some examples on your own as well, because this is really something that just gets better with practice, I think. All right, so let's talk a little bit about the system for naming alkanes and just actually naming organic molecules in general. We are going to be learning in today's lesson the current IUPAC system. IUPAC system for naming organic molecules. And IUPAC stands for the International Union of Pure and Applied Chemists. And just if you're curious, this International Union of Pure and Applied Chemists, they basically set all of the rules for naming everything in chemistry. So in grade 9 and 10, whenever you learned how to name ionic compounds and molecular compounds, Those rules were set in place by this International Union of Pure and Applied Chemists, by IUPAC. They also decide on what the names will be for different elements on the periodic table. And then they also set the rules for naming organic molecules as well. Okay, and I'll just mention as well that we're learning the most current system in today's lesson. The rules actually did change a few years ago, so part of the reason why you have a brand spanking new textbook this year is because we needed textbooks that have the current naming system. The old textbooks had the old system, and Mr. Beatty just felt that, it was time to get some new textbooks that had the new system. So we are going to be learning the most current system today. Now, in any organic molecule name, there is always three parts. Okay, and so those three parts are the root, the prefix, and the suffix. The root denotes the number of carbon atoms in the longest continuous chain of carbon atoms. So we're going to see in a minute how that works. The prefix gives the positions and names of any branches from the main chain. And then the suffix indicates the series to which the molecule belongs. And so this lesson is all about naming alkanes. And so the suffix for alkanes is ane. And this means basically that in any of the molecules that we're going to be naming in today's lesson, they all end with ane because they're all alkanes. All right, now you'll see that in the remainder of the first page, there's just basically a bunch of rules, and it just writes out all the rules that we need to follow in naming organic molecules. And I wouldn't blame you if, when looking at this, you might feel a little bit overwhelmed and think, my goodness, this is a lot of rules to remember. But I think you'll probably find when you actually get doing some examples, it's not as daunting as it looks. It just looks terrible whenever it's all written out. Whenever I taught this lesson to grade 12 university chemistry students in the past, I didn't actually explain the rules before doing any examples, because I imagined that, reading through these rules would not really be helpful without any context, unless you have a chance to see how the rules are actually put into practice. So I'm actually even not going to explain the rules at all right now. We're just going to go straight into our first example. Okay, and you can see that I actually wrote here, that's a lot of steps. I think that it's easiest to learn how to name organic compounds simply by doing a bunch of examples. As I said earlier, this is something that I really think you get better at with more practice. So we're just going to go straight into our first example. And as I said, all of the rules are written in this handout for you to refer back to, but I don't think they're that helpful until you've actually done some examples to see how it works. Okay, so we're going to go through 4 examples in total. And in each of these examples, there's something a little different that we need to know to name them. Okay, so I've chosen these examples specifically because we need to understand all of the rules that are outlined in order to name all of these. So we're going to go through them one by one. All right, so here's our first example. You can see that we do indeed have an alkane here. And this is a branched chain alkane. So we kind of have a main chain of carbon atoms, and then there are some side groups coming off the side. Now, the first step in naming alkanes, and really in naming any organic compound, is to first identify the longest continuous chain of carbon atoms in the molecule. Okay, and in this particular example, you can perhaps see that the longest continuous chain of carbon atoms is this chain. And let's count how many carbon atoms are in the chain. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 carbon atoms in total. And just for clarity, I will highlight that main chain. Okay, so this is our main chain of carbon atoms. Now, you might point out that there are other continuous chains of carbon atoms in this molecule. You could just as easily imagine this to be a continuous chain. And in that chain, we have 1, 2, 3, 4, 5, 6 carbon atoms. Okay, so that is a continuous chain of carbon atoms, but it isn't the longest continuous chain in this molecule. Okay, and so the rule here is to identify the longest continuous chain. And in this molecule, the longest continuous chain consists of 9 carbon atoms. And so that means that our root is going to be non for 9. Okay, and I know that the root is non because if I just go back to the front page here, you can see that if we have 9 carbon atoms, that the root name is non. Okay, so non means 9. I'll just write that down. Okay, so our root is going to be non. So that's the first step. Now, in this organic molecule, there are some side groups. So let's talk about what these side groups are called. We have a side group here to start. So this side group is what we call a methyl group, and I'll write that down. This is a methyl group. Okay, and you can perhaps guess where that name comes from. It's called a methyl group because it is similar in a way to a methane molecule. So I'll just draw what a methane molecule looks like off to the side. So a methane molecule is a carbon atom bonded to 4 hydrogens. So we have a central carbon with 4 hydrogens attached. Okay, now of course this isn't really what we have here though. What we have for a side group is basically a methane molecule but with a hydrogen atom missing. So if I just erase one of our hydrogens, then what remains here is what we call a methyl group. Okay, now of course in the structural drawing that we're given, it's not really explicitly showing the carbon-hydrogen bonds. So it's just showing CH3 to indicate that we have a carbon bonded to 3 hydrogens. The drawing that I made is kind of explicitly showing all of the bonds that are present. Okay, so this is what we call a methyl group. I'll just erase that. Now you can perhaps guess that if the side group that I've circled is called the methyl group, that this side group with 2 carbon atoms, instead of being called a methyl group, it would be called an ethyl group. So this is an ethyl group. Okay, and then the last one, of course, is also called the methyl group. Okay, so these are basically the side groups that we have in our molecule. We have 2 methyl groups and an ethyl group. And it's in the prefix of our organic molecule name that we specify what side groups are present, as well as where the side groups are located on the molecule. Now, in order to specify where the side groups are located on the molecule, we need to number the carbon atoms that are in the main chain. And there are rules on how we number the carbon atoms. And so the rule is that we number the carbon atoms so as to give the side groups the lowest possible number. Okay, so I'll show you how that works. I'm going to number the carbon atoms from left to right so that the leftmost carbon atom is number 1, followed by number 2, 3, 4, 5, 6, 7, 8, and 9. Now, whenever I have the carbon atoms numbered in this way, our methyl group is bonded to carbon number 3. So if I just make a list of the numbers for the side group, the methyl is bonded to carbon 3. The ethyl group is bonded to carbon 4. And then the other methyl group is bonded to carbon 5. Now, I have numbered the carbon atoms correctly here because 3, 4, and 5 are the lowest possible numbers that I can get. If I numbered the carbon atoms the other way instead, I would get larger numbers, and so that would be an incorrect way to number them. Okay, and just to make that point clear, I'll show you what I mean. So now I'm going to number them incorrectly. So, maybe don't write this down because it's just to make a point here. All right, so if I numbered the carbon atoms the other way, if I numbered them instead from right to left, then we'd have 1, 2, 3, 4, 5, 6, 7, 8, 9. And so in numbering them this way, you can see that we have a methyl group bonded to carbon 5. And then we have our ethyl group bonded to carbon 6. And then we have our other methyl group bonded to carbon 7. And so you can see that whenever I number the carbon atoms in this other way, the numbers are higher. So we have 5, 6, and 7 instead of 3, 4, 5. And so the IUPAC rule is that you number them in a way that gives the carbon atoms the lowest possible number. Okay, and so this numbering from right to left is incorrect because it gives the larger numbers. So I'm going to erase our incorrect numbering. Okay, and I'll just write in our correct numbers again. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. So now that we've numbered our carbon atoms in the main chain, we can specify where our side groups are located. And it's really in the prefix of the molecule's name that we specify what side groups are present as well as where they're located on the molecule. So there are rules for this. I'll just write out the prefix first, and then I'll explain the rules that I followed in order to arrive at that prefix. Okay, so just going ahead with the prefix here, we would have 4-ethyl. And then 3,5-dimethyl. Okay, so that is our prefix. It is 4-ethyl 3,5-dimethyl. And I'll just make a comment that the reason, by the way, why I wrote my root so far off to the side here is because I knew that the prefix was going to be quite long. If I had written this non towards the left, I wouldn't have had room to put in this prefix. So that's why I like to leave myself some space. I write the root off to the side. And yeah, maybe just to close up this gap between the prefix and the root, I'll just move our prefix here. Okay, so this is our prefix. It's 4-ethyl-3,5-dimethyl. And there were some rules that I followed when writing out this prefix. So the first rule that's probably obvious to notice is that the number for each side group precedes the name of the side group. So for example, we have 4-ethyl in the prefix. This is simply saying that we have an ethyl group bonded to carbon number 4 in the main chain. And then we have 3,5-dimethyl. So this is saying that there are 2 methyl groups on carbons 3 and 5. Now, another important rule that I followed is that I put the side groups in alphabetical order. So ethyl came first because E comes in the alphabet before M. And so that is why methyl came second. So ethyl is always written before methyl because E comes before M in the alphabet. And the fact that there is a di in front of methyl does not matter. Okay, I purposefully chose this example because it had the di in front of methyl. It doesn't matter that there's a di. Methyl will always come after ethyl when we're writing out the prefix because M comes after E in the alphabet. So that's another rule. Okay, so we have 4-ethyl-3,5-dimethyl-non. This is not the finished name. We do need to put our suffix at the end. And in any of these examples, it's quite simple. The suffix for any alkanes is -ane. So our full name is 4-ethyl-3,5-dimethyl-non-ane. 4-ethyl-3,5-dimethyl-non-ane. Okay, it's kind of a weird name, but that's what we arrive at when we follow the IUPAC rules. Okay, so we'll do example 2 next then. Now, example 2 is given to us as a line structural drawing. And we talked a bit on Friday about how line structural drawings work, but I'll just explain them again. So line structural drawings are actually really nice. They're a very simple and compact way of depicting organic molecules. And in a line structural drawing, it is understood that there is a carbon atom at the end of every line. Okay, so in this line structural drawing, I can tell just from looking at it that we have a carbon atom here, and we have a carbon atom here, and here, and here, and here. Everywhere that a line ends, we have a carbon atom. Okay, so everywhere that I've drawn a dot, we know that there is a carbon atom. And in a line structural drawing, there is no attempt to draw any hydrogens because it's just understood that every carbon atom is bonded to as many hydrogens as needed to complete all of its bonds. Okay, so if I just be maybe a bit more explicit here. So if there's a line ending in these two places, we have carbon atoms there. And although they are not drawn, these carbon atoms are definitely bonded to hydrogens, and they're bonded to as many hydrogens as needed to have all 4 bonds. So our carbon atom at the end, for example, has used up one of its bonds because it's bonded to a carbon neighbor. So this carbon atom must have 3 hydrogens bonded to it for a total of 4. So if I just draw that, we have 1, 2, and 3 hydrogens. Okay, they aren't drawn, but we know that they're there. Likewise, this carbon needs to have all of its bonds filled. This carbon is bonded to 2 carbon neighbors. So 2 of its bonds are used up. And so that means that it must have 2 hydrogens attached, like that. Okay, now I understand like line structural drawings might seem kind of strange, but once you get used to them, they are actually very nice. It's just a very quick way of drawing an organic molecule. Okay, but just to clean things up a bit, I'll just erase that. All right, sweet. So these are all the carbon atoms in our molecule. And so we'll begin with our first step in naming this molecule. You might remember in the previous example that we started out by identifying the longest continuous chain of carbon atoms. So in this example, you can perhaps see that the longest continuous chain of carbon atoms would be right along the center here. Okay, and how many carbon atoms do we have in that chain? We have 1, 2, 3, 4, 5, 6, 7, 8. Okay, and maybe I'll go ahead and highlight our main chain. All right. So yes, we have 8 carbon atoms in our main chain. And so in following the rules that we learned about before, that means that the root for this molecule has to be oct. Has to be oct. Oct for 8. Okay, so there are 8 carbon atoms in our main chain. And you can see that we have a couple of side groups. If you've been paying attention, you would know that this is a methyl group and this is an ethyl group. Now, in the prefix of the molecule's name, we need to specify which side groups are present as well as where they're located. And so you may remember in the previous example, we numbered the carbon atoms so that we can specify where the side groups are. Now, if you try numbering the carbon atoms in this example, you might see that we run into not really a problem, but just it doesn't work out as nicely as in the previous example. Okay, and I'll show you the issue here. If we number the carbon atoms from left to right, if I just fill in 1, 2, 3, 4, 5, 6, 7, 8, then you can see that our ethyl group is attached to carbon 4. And then our methyl group is attached to carbon 5. Now, if we number the carbon atoms the other way instead, let me just erase this. The side groups actually end up getting the same number. And this does happen sometimes. So to just be clear, if we number instead from right to left, we'd have 1, 2, 3, 4, 5, 6, 7, 8. Okay, and so here we have a methyl group that's attached to carbon 4, and then we have an ethyl group that's attached to carbon 5. And so things are not quite as simple as in the previous example, because it doesn't matter which way we number these, the side groups are given numbers 4 and 5. Okay, and you can perhaps guess that I purposefully chose this example because it doesn't matter which way you number them, you get the same numbers for the side groups. So what do we do in this case? Well, IUPAC does have rules for when this happens, and the rule is that in these cases where the side groups get the same number, no matter which way you order the carbon atoms, you give the side group that comes first alphabetically the lowest number. Okay, and I'll just say that again. You give the side group that comes first alphabetically the lowest number. And so in this example, our side groups are an ethyl group and a methyl group. Now, ethyl comes before methyl because E comes before M in the alphabet. And so that means that we should number the carbon atoms so as to give the ethyl group the lowest possible number in this case. Okay, and so that means, in fact, that the way we have it written now is wrong, because our ethyl group, which comes first alphabetically, is being given the bigger number. So I'll just erase this incorrect numbering and number it correctly. All right, so this is the correct way to number our carbon atoms. And so based on what we learned in the previous example, perhaps you can figure out what the prefix has to be. So we gotta put our side groups in alphabetical order and specify what number on the main chain they are bonded to. Okay, so in this case, our prefix is 4-ethyl. For ethyl, 5-methyl. Okay, and as before, I will just close our space here. All right, so we're almost done. You might remember, though, that we need to put our suffix at the end as well. So since we are dealing with an alkane here, we just put an ane at the end. Okay, so this example is 4-ethyl 5-methyl octane. That's the name of our molecule. All right, let's do example 3 now. All right, so example 3 is what we call a cycloalkane. Okay, and I purposefully chose this example so that we can learn how to name cycloalkanes. A cycloalkane, you may remember from Friday, is simply an alkane that has the carbon atoms bonded into a ring. And so we can see in this example that we have 4 carbon atoms bonded into a ring. Okay, so there are 4 carbon atoms bonded into a ring here. And we do also have some branches off to the side. This one consists of 2 carbon atoms. And then this one consists of 3 carbon atoms. And so in this example, since our ring contains more carbon atoms than either of the branches, the ring would be in the root for this molecule's name. Okay, so our ring has 4 carbon atoms. That is larger than 3 or 2. So that's why our ring becomes part of the root. Okay, now you might wonder, like, okay, Mr. Musklo, what would happen if this branch instead had 5 carbon atoms? Well, then things would get a bit more complicated. In that case, the branch would end up becoming part of the root, and then the rest would be considered a side group. But I'm going to be honest with you guys, like, I'm not going to give any examples that involve that. You can actually think of tons of, like, examples that would involve using rules that we haven't learned. And I just don't want to overwhelm students with a million rules. So yeah, we're only going to consider cases like this, where there are more carbon atoms in the ring than there are in either of the branches off the side. Okay? So, given that our ring has more carbon atoms than either of our branches, that means again that our ring is going to be our main chain. It's going to make up the root of the molecule's name. So let me just highlight that, as I've been doing. Okay, so this is our main chain. All right. So we have a ring for what will be in the root name of our molecule, and it consists of 4 carbon atoms arranged in a ring. And so the root that we would use in this case is cyclobute. So I'll just write that out. Cyclobute. Okay, so this is simply saying that we have 4 carbon atoms arranged in a ring with some side branches coming off the side. Okay, so that would be the root in this example. Now we also have some side groups, of course, so we need to specify where those are. And so we need to number our carbon atoms. Now, this example is kind of similar to example 2 in that there's more than one way to number the carbon atoms so as to give the side groups the lowest possible numbers. Okay, so I'll show you how that works. Let's begin by trying to name our carbons in a clockwise direction. Okay, so if I labeled this carbon number 1, and then this one 2, this one 3, and this one 4, then you can see that this side group would be attached to carbon 1, and then this side group would be attached to carbon 2. Okay, but here's the thing. You can actually also number the carbons counterclockwise and still give the side groups numbers 1 and 2. Okay, so this is numbered clockwise. I can also number them counterclockwise instead. So if I start out on this carbon, we would have 1, 2, 3, and 4. And this would also give our side groups the numbers 1 and 2. Right? Because this side group would be bonded to carbon 1, and then this side group would be bonded to carbon 2. Okay, so we need to follow the same rule as we did in the previous example. In the previous example, we saw a case where we could number our carbon atoms in two ways, and both of those ways gave the same numbers to the side groups. So in these cases, we number the carbons so as to give the side group that comes first alphabetically the lowest number. Okay, so in this example, we have an ethyl group. Ethyl starts with E. And then we have what's called a propyl group. And propyl starts with P. And so our ethyl group comes first alphabetically because E comes before P. And so that means that we need to number our carbon atoms so that the ethyl group is number 1. Okay, so I actually have this labeled incorrectly. It needs to go the other way. Okay, so our ethyl gets the smallest number because it's first alphabetically, followed by propyl, 3 and 4. Okay, so we have our carbon atoms numbered now. We can write out our prefix. So the prefix would be 1 ethyl, and then 2 propyl. And I'll just move it again. Okay, and then of course we need to put our ane suffix because it is an alkane. And so that's our correctly named example 3. It is called 1-ethyl 2-propyl cyclobutane. All right. And then our last example is example 4. And I'll go through this one a bit more quickly because, it can be a lot of information to take in, and I don't want this video to be too long. This example, I think, is actually pretty simple, given the rules that you've learned so far. So in this example, we have a chain of 5 carbon atoms. And so our longest continuous chain of carbon atoms would just be that chain. It would be 5 carbon atoms long. Okay, so I'll highlight it as we've been doing. All right, now we have 5 carbon atoms in our main chain. So that's going to make our root. If we have 5 carbon atoms, then the root is pent. So we have a pent. Now you can see that we do have some side groups here. If you look closely, you can see that we have some bromines that are bonded to our carbons. And in our prefix, we need to specify what carbons those bromines are bonded with. And so we're going to number our carbon atoms so as to give those side groups the lowest possible numbers. Okay, and so in this example, that would mean numbering the carbon atoms from right to left. If I number them from right to left, we have 1, 2, 3, 4, 5. Okay, and so we have a bromine that is bonded with carbon number 1, and a bromine that's bonded with carbon number 3. Now, whenever we have bromines bonded to carbon atoms in an alkane, we call them bromo groups. And so this would be the prefix for example 4, would be 1,3-dibromo. 1,3-dibromo. Okay, and then of course, we need to put the ane suffix to just make clear that this is a molecule without any double bonds. Okay, and so that's it. We have 1,3-dibromopentane as our last example. Okay, so just to kind of wrap things up, I'll mention again that I understand there's a lot of rules to remember. I really do think that naming organic compounds is something that you just get better at with practice. So I certainly wouldn't expect any students to be able to do examples perfectly now, just given, like, what you've been explained so far. In order to get good at this, you really need to do examples on your own. Okay, so my suggestion is to just get really good at this, to just do a bunch of examples. It's kind of like math. If you're just explained a math concept, you probably won't be able to apply it right away, but the more examples you do, the more confident you'll feel in your new skill. Okay, so hopefully you like that, and you can almost treat it like you're solving some puzzles, because it is almost like solving puzzles in a way. For that reason, I think this is kind of fun. And yes, in our next lesson, we're going to learn how to name alkenes and alkynes. So to give you a heads up, alkenes are molecules that have double bonds, and alkynes are molecules that have triple bonds. So that's coming next.